Okay, so in this video, I'm going to take the plunge and try to derive Euler's formula for you. And I'm not sure that I'm going to be able to do it. It's been a while since I've done this. So the goal here, ignore this for a second. The goal here is to derive this formula, which is often written, it's written in a couple different ways. Sometimes like this. And sometimes it is written e to the I pi equals -1. Now in the previous video, hold on, I'm pushing the wrong buttons. In the previous video, I talked about imaginary numbers and eventually got to this point where I described this little thing, that this is a very nice package for describing rotation. So let's see, this part, I'm getting confused. This part, whatever. Right here is, you've got a rotation, you've got the theta here, which is rotating, and the r is scaling. So it's very useful, neat little package, and I would like to use it in my videos, so I figure I might as well try to explain it at some point. So it looks like I was drawing on this thing, but anyway. So -1. So that's the goal, is to derive this kind of thing. Now, there's something before I start, which is sort of more obvious, but it might look strange at first, that we can describe some complex number, z, with this setup right here. So basically, because we were looking at a coordinate plane, we were describing z as being somewhere in the complex plane. So this is just sort of a geometric way of looking at a complex number. So let's say there's z, and so actually it should be, we actually need an r times here. So hold on. We actually need some kind of number. It's actually the modulus right here times this stuff. But so if the modulus were 1, right, then it was just this, there's no r. So if this were length 1, then this right here is cosine theta, and this right here is sine theta. If this doesn't make any sense right here, then look at previous videos that I've made. That's theta. That's beautiful theta right there. And yeah, so I've talked about how if you have a unit circle like this, unit that this is length 1, that this will be cosine and this will be sine. So if this were 1 instead, okay, then it's just some amount, the real amount is cosine theta, and the imaginary amount is this sine theta. So it's just another way of representing it. But if it's not 1, we just multiply everything by this r. And this will be r sine theta. I should have given myself more space. And this will be r cosine theta. Everything just multiplies by r. So this is another way of representing complex numbers. And so it's good to go through the math in high school and learn polar form and learn complex numbers and, you know, get lots of practice, because that's the only way that this becomes sort of obvious. Now we're going to make use of this formula, which is Taylor's theorem, and we're going to make use of calculus. So this is kind of the starting point. So I don't know if I'll make a video about deriving Taylor's theorem, but it's sort of, so it's a way of approximating something, and you start at the, so we have some function, and so it's like this, and we have some x0 value. So we start with the value at x0, and then we take into account the first derivative, which accounts for the slope. Here's how I'm representing the slope times this stuff, and then we account for the second derivative. And every time we account for further and further derivatives, sorry I bumped the mic, but every time we account for further and further derivatives, we get more and more accurate as to what this value is. Anyway, I have to start somewhere, right? And I want to derive this thing, so this is the starting point. Maybe I'll have to go back and explain this further some other time, but we have to start somewhere. And we will be making some use of calculus. So where do I want to start? Well, I want to start with the function e to the x. So we'll say that our f of x here is e to the x, and we're going to be using this formula. So let's see, where am I going to write this? Well, let's do the first term, and let's do this. Let's just say x naught equals 0. We're going to take this at the value at the origin. So I guess this approximates the entire function, not just at a value. So we plug in 0 here, and we get e to the 0 equals 1, right? So that'll be the first term. So okay. F of x equals e to the x equals, we're going to start with a 1. That's the first term. Then we're going to take the first derivative, and then we have an x minus x naught. Well, we said that x naught is 0 here. So that'll be x minus 0. So that's just x over 1 factorial. So first derivative times x. I'm making it look incorrect here. So anyway, what's the first derivative? Well, when we take the derivative of e to the x, it's just e to the x. That's the beauty. That's why we love e to the x. So it's plus, so it's e, and do we plug it in? Let's see, f, yeah, we plug it in again. So again, we're plugging in e to the 0, which is 1. So we get a 1 for the first derivative here. And it's going to be multiplied times x over 1 factorial, which is just 1. So we just get x for that part. Then we do the next step is the second derivative, which when we plug in 0, the second derivative is again going to be e to the x, and this it will always be e to the x no matter how many times we take the derivative. It doesn't change. And we keep plugging in 0 each time. So these just sort of disappear. They're just 1. And x minus x naught is just going to be x. So it's x squared, x cubed, and so on. So what we're going to get is, and I'm actually just going to go back a bit and write x here. For the next term, we said we get x squared over 2 factorial plus x to the third over 3 factorial plus dot dot dot. So this is our, I think, I forget if it's called a Maclaurin series now. I mix up, and other people also mix up, like Taylor and Maclaurin, kind of a similar thing. But this is now, I think maybe it's called Maclaurin series. A Maclaurin series for, or maybe it's Taylor, I don't remember. But it's an expression for e to the x here. Okay, so we have, whenever we're using e to the x, we could also use this expression. So if I have an e to the I theta, right, which is, I suppose, an interesting idea. If you're looking at this formula, maybe, hey, we'll plug in an I theta for, maybe I'm mixing things up. Maybe it's, I'm trying to give a justification. Anyway, Euler was a genius and he decided to calculate this. So what happens? We get 1 plus, in place of x, we have I to the I theta here. So I theta plus I squared theta squared plus blah, blah, blah. I cubed now I think I'm going to need to do the same kind of thing for cosine and sine to show you how those play out. I think, like I said, I'm not it's been a while since I've done this. But so now let's say f of x is cosine, and we're going to use Taylor's theorem to find some way to calculate this. So it began with the first derivative. No, began with f of x naught. So let's choose theta equals 0 as our x naught. So cosine of 0 is 1. So that'll be our first term. So we get 1 plus, then we're going to take the first derivative. Okay. And this will be, again, I'm getting a little confused. But now, so the derivative here is going to be negative sine. That's the derivative of cosine. And we're going to plug in a 0, and we get 0. So the next term vanishes. Okay, and then the next term is going to use the derivative again. So we take the derivative of this, we're going to get negative cosine of 0 equals negative 1. And then I'll just do the next derivatives. The next one is going to be positive sine of 0, which is 0. And if we take, did I do that right? Sine. And then the derivative of that is going to be back to cosine, which is back to 1. So it cycles. It's like a cycle of order 4. Okay, so we skipped the second term because it was 0. So the third term, it starts with a negative 1. This third term, the third derivative, evaluated at 0. We chose 0. So that's going to be a negative 1. Let's just write it out. So it'd be a negative 1 times, it was x minus 0, right? Cubed over 3 factorial. So then the fourth term is going to be 0 because of this, and the fifth term is going to be, there's a positive 1. So this was minus, it'll be plus, it'll be x to the fifth over 5 factorial, and just do plus dot dot dot. Okay, so let's write it out a little neater. Minus x cubed over 3 factorial plus x to the fifth over 5 factorial dot dot dot. Okay, now we need to do the same thing for sine. So sine theta. Okay, so first we're going to use 0 for x naught again. So we're going to take f of 0. Sine of 0 is going to be 0. So we're going to need the derivatives, so I'm going to write this out again. So sine of 0 is 0. And it's actually the same pattern, it just starts here, right? So it's going to be the same cycle. So we get 0 for the first term, and then the derivative is going to be cosine of 0 is 1. That's going to be 1 times x over 1 factorial, right? Then we take the next derivative, which is again going to be 0, and then so that next term will not be around. And then actually there was a negative here, and there's a negative here, and we get negative 1. So you can see these are alternating, same kind of pattern. And so we're going to have this minus 1, right? And then x to the third over 3 factorial. And then the next term is going to be x to the fifth, plus x to the fifth over 5 factorial, dot, dot, dot. Okay. Now, let's try plugging in I theta for these and see what happens when we just plug in I. But should we do it only... Is it plug it in or or do we multiply it? What's the goal here? This is a little complicated. The goal is we're going to get e to the I pi equals negative 1. So I think maybe we didn't need to do all this. Let's plug in not e to the I theta, e to the I pi. Maybe I did a bunch of unnecessary work, but it was a good exercise anyway. Sorry, I'm kind of new to this software, so don't know what I'm doing. Okay, let's go down here. E to the I pi. Maybe we didn't need to bother with sine and cosine. Maybe that was extra work. So this is the formula here. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So 1 plus x, which is I pi, plus x squared over 2 factorial, so I squared pi over 2 factorial. I'm a little confused. I'm making a guess that I'm gonna plug in I pi here and see what happens to the sine function here. So we get, or rather I theta. So I theta, and with the minus here, I know what we're gonna get. We're gonna get hyperbolic. We're gonna get something totally different. That's not it. Well, okay, let's use this as inspiration, and we'll just figure out what cosine of theta plus I sine theta is. Okay. So cosine theta we have here. Okay, I'll write it out again. It's 1 minus x, was it x squared over 2 factorial plus x to the fourth over 4 factorial dot dot dot, I believe. I think these are supposed to be squareds. I think I made a mistake. This should be cubed. Oh, sorry, this should be to the fourth. That's a mistake. Okay. Let's see. Let's check that. So this was the second derivative, so it should be squared. Yeah, second derivative is squared. Okay. All right. Then for sine, we're going to do I times sine. So I times x minus x cubed over 3 factorial and we're going to add these together. So this is cosine theta. Oh, actually, it's cosine of x here plus I sine of x. Okay. So when I multiply this out, ix, okay, I know what I need to do. I know what I need to do. E to the ix equals, the first term is 1, plus ix. We need to do both of these, okay. Plus the next term is going to be I squared x squared plus I cubed x cubed plus, I'll just write this out, 2 more terms, I guess, so we can see, make sure everyone sees the pattern. I to the 5th, x to the 5th, dot, dot, dot. So it'll be 1 plus ix minus x squared minus ix cubed. I to the 4th will be plus 1, so it'll be plus x to the 4th minus, sorry, plus I x to the 5th. So it's switching every 2 times. Be minus x to the 6th. And I forgot all the, I've left out all of the divided by factorial things. So, over 2 factorial, or 3 factorial. I'm just going to make it messy because we don't, who cares? 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Okay. Now we compare this to this stuff over here. E to the ix. And it should be cosine x plus I sine x. Okay, so do you see that? So we have, how about we label the cosine and sine terms? So I'll label cosine terms here. So 1, 1. Or rather down here, I guess. 1, 1. Minus x squared over 2 factorial is there. Plus x to the 4th over 4 factorial is here. Okay. Then where's the sine terms? We'll do magenta. We have ix. It's going to be, when you add the I, it'll be minus ix cubed over 3 factorial. I made it look like it's in the denominator. So forget about that. We'll put it here now. So ix cubed, or rather minus ix cubed over 3 factorial is also here. Then we have plus I times x to the 5th over 5 factorial is there. So you can see that we're getting, for some reason I underlined it instead of going over, we're getting all the terms. It's switching between the cosine and the sine here. So what this means is, before we saw that you can represent any complex number in this form. So what we're seeing, or well, this is a complex number where r equals 1, where the modulus is 1, right? So we're seeing that any complex number can be written in some kind of form like this in general. And in fact, if we multiply both sides by r, so this is a unit complex number because we said r is 1 here. But if we do a little more general, and let's multiply everything times r, some number, some scalar, ordinary number, then we'll get everything times r, which equals some general complex number. This just means it's a complex number. So what that means is that some r to e to the I something equals some kind of complex number. So you can represent it as a plus bi, or you can represent it as some cosine theta plus I sine theta. So we're seeing is there's all these different ways to represent a complex number. Okay, and we're not quite done yet because we haven't shown these equations to be correct. But what we do now is we plug in pi for x, see what happens. So e to the I pi equals, so now I don't have, I should have had an r, I keep forgetting the r here. But here r is 1, so it disappears. We just plug in, and I mixed theta. I mean, this, I should have written this as an x. But I was saying some theta, it doesn't really matter. It's not technically wrong, just I could have written an x here. Now I'm thinking, did we prove that this x is the same as this x? I think that's what we showed. This x here works out to be cosine x plus I sine x. So that is what we showed. Okay. So we're plugging in I pi, or we're plugging in pi for x in this situation here. So I times sine of, this should have been, okay, hold on. There's lots of room to make mistakes here. This should just be in pi. Yeah, I hope that's right. And so cosine of pi is -1. Sine of pi is 0. So we get e to the I pi equals -1. And that if we add 1 to both sides, we get e to the I pi plus 1 equals 0. Okay, so I think I roughly did everything we were supposed to do. Hopefully I didn't make too many mistakes. I didn't really explain Taylor's theorem, like how to derive it, but I think, you know, in terms of starting somewhere and stopping somewhere, you know, I think it was okay. I also wasn't very confident, though I did get through it. So maybe I can get a little better, practice a bit, think a bit, understand better, and make better content of this kind. But cut me some slack here. This was this was a bit of a doozy to do. But now we have this wonderful thing where we have some r times e to the I theta we can use to represent some complex number. So you can think of this as a map, which a map also is just a function. So we can take, well, it's more than just a map, because it's saying any complex number can be represented in this form with some r and some theta. Just to be kind of complete here, I'll write this out, that z is a complex number and r theta, well, theta is an angle, but we can have any real numbers there. Okay. So this is very useful. It gives us a very useful representation, because this r tells us how much this scales by, and the theta tells us how much to rotate by. because this will always be represented with this triangle. There's a theta here. Assuming, let's just say r equals 1, just for simplicity, because if r doesn't equal 1, you're just scaling the same picture up or down. That's all. So we'll say r equals 1. And so this is sine theta. And this is cosine theta. And so clearly theta is the argument. So e to the I theta maybe I'm going around in circles or something, but I think this is circular logic. But we proved it above. We proved this. We did it with x, but it's the same thing. So yeah, it's not circular logic. I'm so used to this that it becomes hard to like undo in my head that this is not obvious. I don't mean that as a brag. It's just I've been sort of as a hobby studying physics for like 10 years, and this is used quite frequently in more advanced physics. So I think we proved what we wanted to prove, and that we have this wonderful form that we can use. I'll call it Euler's form. I don't know if that's the Eulerian form or Euler's form for the for this I theta that will be useful sometimes. But this is not really for programming. This is for physics past. If you get just past an introductory course in physics, and also it's useful in advanced mathematics. So now we have this here on the channel to use, and maybe let me know if you want a video about this Taylor's theorem or just about calculus in general, because those were sort of prerequisites here. Yeah, let me know. Thank you, and have a good one. Bye-bye.